Hello everyone. So this lecture I'll be talking about the generators of groups and on the primitive roots and the discrete logarithm. So first I begin with what a generator is, a group. So we earlier defined, so I think we defined it earlier somehow, but exactly. So we say like this group with this notation means so the elements generated by A. So here it's the elements generated by A, so it's basically the powers of A, and so on until A to the power n minus 1. Or I think here I'll use K, so it will be a bit clearer later on. So here we have like the size of this set is equal to K, and this is like the number of distinct elements, and we know by that A to the power of K is equal to the identity element and so on. We also know that this group, this set can form a subgroup of the original group. Uh, if we have some group G and S and some operator, then we have that this is a subgroup of, and this is a subgroup of G. So yeah, where A is one element in S. We just take from the main group some element and take its powers. It has to form a subgroup. Uh, so next we move this to be. Oh yeah, there's also another theorem that we can prove here about the size. So we just apply the Lagrange theorem. Here we have the size of the group G is equal to M. And we have some elements generated by A. This has the size K. So as we said, this is a subgroup. So basically, we have by Lagrange theorem that K divides M. All right. This we will need later on. Then we move to the next part. So what is a generator? So if we have a group G, we say like from A is generator of G. So this will happen only if here this element is the set. So basically the set generated by A is actually the set of all elements. Yeah, we'll come to examples about that. So here this shows there's an indication that here the size of this is equal to K and this is equal to M. So the sizes need also to be the same. So we move this into the context of the multiplicative group modulo M. I explained earlier. So this group, some notification. So just write the definition again. So it's the elements A such that A is greater than 1, less than n, and A and n are co-prime. It's the same set that we used to do before. And we have also Euler's theorem that says something like this. So A, and we have the size of this set to be 5n. So basically you have A to the power 5n equal to 1. Using this multiplication operation here that makes a multiplication and then take a remainder when we divide by n. So here to compare, here so here the G is our set now. So it has a size m. So this m here is our phi. So this is the m that we're using. So here we would say we define what is called the primitive root of this group. It's one generator of this group. So basically, it's an element. Let's call it G, such that when we generate the G, this will get all the elements in this set. So, for example, we can here. If we look at, let's say, a multiplicative group, not 13. So this has all the numbers from 1 to 12. So let's, for example, try to generate the 2. So the 2 will get 1, 2, 4, 8, and 16, which is 3, 12, so 12 to 11. So and then we get 9, and then 5, and then 10, then 7, and then 1 again. So basically it starts to repeat here. So here we find that all the powers of 2 are generated. So these are the powers of 2. It's not here, so this is 2 to the power 4. So this is 16, and it's 3. And we take remainder with 13, and so on. Keep multiplying by 2. So it keeps going like that. So here we find that the 2 is a generator of this set. For example, if we try something like, say, the 4. So does the 4 generate the set? And try to do it. So 1, 4. I'm sure this should be. So it's 16. So basically it's 3. 3 times 4 is 12. And we keep going like that. 9 times 4 is 6. Now probably I did some mistake around here, so 3 times 2, 12, 11, 9. Oh yeah, it's not a mistake, this is a 5. So here the 4, we find that it doesn't generate the whole set, so 4 is not a primitive root. So here the 2 is a primitive root. So the primitive root will have this property that it's g, then g to the power, so the size of this set, and this will be equal to 1, which also we know from Euler's theorem. However, the g to the power k will not be equal to 1. K is less than 5n. So basically this will give an idea how we can find the primitive root, or let's say to test if a given generator or a given number will actually be a primitive root or a generator for the whole group. So how do we check that? We get back to this part here. So here we have from this part that the size generated by some element A. If it's k, then this k has to divide the whole size of the group. So first I'll do it for any group, and then we'll see how it works in the primitive, meaning the multiplicative groups, modulo n. So in groups in general, here we have like if this g, sorry, this A has so some size k. So we already know that a to the power k will be equal to e, with the identity element. And yeah, k has to divide n. So basically, and we also need to prove another property. So for any number a, so if we raise a to some power, and this power will be equal to e, then we must have this s as a divisor of the power. And let's say that, sorry, so this s will be a divisor of m, because from here we can have this property, which means that whenever we have here that a to the power of s equal to e, it means that the group generated by this has a size s, or so that this is assuming that the s is the smallest such a number. So if s is the smallest number, then this set generated by a has a size s, and then we know that s divides the n. So it means that the size s, and then s divides n. So basically, we can from here just use the divisors of m and check if one of them is satisfies this inequality. we know that a to the power m is equal to the identity element. So we can check if this is equal to e or not. Because basically this is the way that we can find any repetition. If we try for all the divisors of m, so we have to try for k that divides m. So we check here if this number, which is a number that divides the m, this divides m because we have m over k. This is equal to an integer, this k basically. So this number divides the m. So if this is true, and it means that this number doesn't generate the whole set because it has a size that's smaller than m. So here we find all the divisors of m, and we try to check if this value is equal to e or not. If it's true for any divisor, then it means that a is not a generator. Yeah, I think I will take one. Yeah. So this is basically how we find if a number is a generator or not. And here also have to make sure that the k is not equal to m, so it has to be a proper divisor, not equal to m and not equal to 1. Sorry, not equal to 0. No, 1. Because if k is equal to 1, then this already is satisfied trivially by Euler's theorem. And yeah, we can actually allow k to be m. Actually, we don't have that. So here we have to exclude the k equal 1 because this will make this equation satisfied trivially by using Euler's theorem. And if k is equal to m, then we already assume that the a is equal to the identity, which is not what we will be using usually. So it's clearly that if the a to the power of 1 is equal to e, then it will not be a generator. So this is how we go, and actually we don't need to check all the divisors of m. It's enough to just check the prime divisors of m because of the following property. Let's say that there are some prime that divides k, and this k divides m, such that a to the power m over k is equal to the identity element. So here we can have, so we can substitute this. So this would be s times k, and k would be, say, q times p. That's one. So here m over k is equal to s. But however, we can also check like m a to the power m over 2. So check m over p. This is equal to s times k. Uh, so this is equal to k. And basically here we have that a to the power of s raised to the power of k. And the s here is equal, so this is, so this value. So this is a to the power s. So here we have that is equal to the identity to the power k. So this is equal to the power to the identity. So here we have like, if for some divisor k, we have this equality true, then it will also be true for any prime divisor of k. So we can just try all the prime divisors of m and check if this equality is true or not. So if it's not true for any of the prime divisors, then we can say that this A is a generator of the group, otherwise we say it's not. So we can come to this in the context again of the multiplicative groups. So here basically we check for A pi n divided by t and going from n or not. So if it's true, then it means that A is not a primitive root. And the false is otherwise. So it means here it's a primitive root. And basically here this P has to be all, we have to try for all the prime divisors that divide 5n, which will share a lot of the like prime divisors of n, but not all of them. And also, so there's still some, like we have to factorize this number and so on. Like later on we can find that this number here and the n, they would share a lot of common divisors, most probably, but still it's tricky to handle that, so we're not getting into that. Basically, this finishes the first two points. So like we have to mention also another point that so not every multiplicative group has primitive roots. For example, something like the 15, which we had earlier, had the elements 1, 2, 4, and 7, and 8, and 11, 13, and 14. So this is the group, and basically we have so all the subgroups are, so the generators we generate using the 2, we get the elements 1, 2, 4, 8. We generate with 4, we get 1 and 4. And we will keep getting always. We generate with 1, get 1. We generate with 8, get 1, 4, 8. 15, so 8 is 4. 4 and 8. Actually, put that and so on. So the 7 will generate 7, and then 7 squared is 49, which is 4. And then this times 7 would be 2, which is 13. And then you get here we have the 1. Here will be just that. And like we can keep going. It will always be size either 1 or 2 or 4. So the numbers that can have some prime divisor, or sorry, some primitive root, so it has to be that n is in one of these 4. So 1, 2, 4, and 2 times t to the power of r, or t to the power of r, where t is odd prime. Here there's a sequence, all the numbers that have primitive roots. So here, for example, you can find the 15, also the 16, and so on. See, here we can look. Usually it's Notch website that has a lot of sequences and some properties about them. So we can write actually a code that finds a primitive root. So we try to find it simply by brute force. It's a number that prime divisor. And actually just use the smallest. You can use the sleeve of the, it gets like the small factor. Here we get the smallest factor, and Here we get, so here we have some prime divisor, this number, which is basically some prime divisor of pi. And here we'll try mod some a and for pi p and n. If this number here is equivalent to 1 mod n, then basically we'll say that this a is not equal. Here we have to actually look for all the a's. So here we'll make it by trial and error. So we go through all the numbers and we check if they are a root or not. And if they are, then we just return the first one we find. Here means we have a flag that we will check. So if it got false here, it means that this number is not a root or not a generator. So this flag is true, then we can return it's a, otherwise we need to run it down. And also common from here. So this should be an algorithm to check like to find a primitive root of n. Basically, we go through all the numbers a, and then we try to say it could be a generator, and we go through all the divisors. So start with pi, and here we get the smallest factor, which is a prime divisor of this div variable, which is a prime divisor of pi. Here we have to so we can divide by p. Here we will make sure that we go like using all the prime divisors. So if this flag remains true, it means that this number actually passed the test and it's a root, so we just return it. Otherwise, we then say there is no number. So the only thing that remains is like completing this try. Here we keep dividing by p, and this pe, which will be eventually the exponent we have. So here we could multiplying this times p. Basically, here we can pe plus p. If n is equal to 1, So I'm doing it recursively. I'm taking one, so the smallest prime factor, and I'm taking the exponents of this, and this is the formula which I explained earlier. It would be actually like that. So this is p to the power of e minus p to the power of e minus 1. And I multiply this by the phi of the remaining number. Here we can something. Here we run the sieve. We go through all the numbers, or we can just say find the root of say 14. And also, after debugging, we can just say here what's the value of phi. Here we can find that the phi of 13 is 12, as we expect it to be, and it, it got the first primitive root, which is 2. Also here we can print which numbers are primitive roots instead of just returning the first one. Here we can just print the A, and then we'll say that here still I keep up in this value right, which is return. So here I keep the first value that I see, so I will still return the first primitive root, but here I will print all the other ones. So you can see some separator here. As we can see here, so the 5, 13 is 12, and all of these are primitive roots. And then this is the first one. Compare, for example, with the 15. So here's something somehow unexpected happens. So here we have the 5, 15, so equal to 8, uh, as we said earlier. Here it found that 3 is 22. So is that. Effectively only find only divisor is 2. Here, oh yeah, section. It's not about. So I needed to check like the A that actually belongs to the multiplicative group. So because the 3 is not co-prime with 15, so we shouldn't check it. As expected, finally. So we don't find any primitive roots of the 15. And here, so all numbers from 1 until let's say 25. Let's find the root of them. And this set. Here we see that the phi has the primitive root 1. When like n is equal to 1, for n is equal to 2, it's the same. For 3, it's the 2. And the 4 is the 3. And so on. We keep going. So the 8 is not on the form that we specified earlier. So it doesn't have square root. Sorry, a primitive root. So the 9 here has like the 2 and the 5. 10 has 3 and 7. And keeps going. 12 doesn't have. 15 and 16 we don't have. And 24 also doesn't have. So this is basically how we find the primitive root of some multiplicative group. And here there's a justification to use this brute force that usually that there's a small enough primitive root that you can find, so you'll actually find it quite fast. So we'll find in the Wikipedia article about this, there's like citations at the end of some research made about how fast we can find this primitive root. But usually when I was solving problems with it, it was like this was good enough. This would get us. So we finish those two now. And we get to the last point, which is the discrete logarithm. So given that we have some number a and a primitive root, which is a generator of the multiplicative group, so we'd like to find the k such that g, the power of k, equal to a. So here we have this theorem that says like so g to the power of k is congruent to a, so it is congruent to g to the power of q mod n. Then this is equivalent that k is congruent to q mod 5n. So this is an important theorem like we have as a property here. So this theorem is true because here we can keep adding any multiple of phi, and it's basically equivalent to multiplying by 1. So it doesn't change the result. So as much as we add multiples of phi to this cube, we still get the same equation. So that's why we have this equivalence here. So to find this, so this was just one theorem. It's not directly related to the problem, but still useful to have. So the next would be solving this this part here. So we could here go through all the powers of G and try to find like which power is equal to A. So this in the worst case scenario would be O of n, where n is the size of the group. So if the G has a size equal to n, then we can try G for 0, G for 1, and so on, until G for n minus 1, and find which G to the power of k is equal to A. And then we just, once we find this k, we just return it. So this is one way of doing it. This has the time complexity of n. So we will proceed to another algorithm, which is called the baby step giant step, which attempts to solve the same problem but in a more efficient way. So this algorithm will assume that this G to the power of k equal to A. So the k, we can write it as some x as x times m. So x times m plus y, where m here is the square root of the group size. So it's the square root of this number. And then we just add 1 to it. So it's this number. So basically, we see that in a number from 0 until n minus 1 can be represented in this form, where x is smaller than m, also y smaller than equal to 0. Because here we can find that xm squared and x plus y. So already we can, using this form, we can represent any number from 0 to n minus 1, and even more, but we don't care that way. So basically, after we substitute with this, we get this form, which is d to the power m, so to the power of x, and c to the power of y. This is equal to a. So g to the power of y equal to a. So basically, you have this here. So if this is true, then we have this this equality. So the way the algorithm would work is that we begin by having some a map data structure, so that would store the powers here. So we store basically g power 0 goes to the t0, and g power 1 go to the value 1, and so on until g power m this goes to the value n. So from here we have like a map that stores all the powers of g until the square root. So as we can see here, we can just try all the numbers on this form. We can go through all of them and check if one of them is a power of g. So by checking if it exists in the set. So if this is true, then we already found the solution, and if we couldn't find them, actually it shouldn't happen if the A. So we should always find the solution if the A is in the set. So we get to use. We call this map like P, like P for powers or something. So we first compute this formula. So it's 3 to the power minus m. We begin, like we have our A, and we try all these values. So A, so A times mu, A times mu square, and so on until A times mu m, and check if any of those occurs in this set P or not. We find it. So here we get, let's say we got so A to the times mu to the power I, and this found the key g to the power j. It found this pair. So basically it means here that we have A to the power g minus m, or I is equal to g power j, and then we have that A is equal to g power mi plus j. So here so this value will be our k. So we can get here, we already know the I because we know where we stopped in this loop, and this j, we already know it from the map. So this is our case, this expression. So this solves the problem that we had, which is basically this one. Alright, so and this we can see, so it has the time complexity. So now it's the square root of n. So O m to the square root, and this is multiplied by the search time in the set. So if it's a preset or something, then we have a log m plus there's an extra m. So this extra m for the putting these elements here. Actually, so we also insert in the complexity as finder. So this will be the complexity, or if this is an unordered set, unordered map or a hash map, something like that. So it will have no m complexity, where m here is the square root. So this is a more efficient way to solve it's called the discrete logarithm. So it's finding the inverse exponent of some number. So we can check how to code this fast. Here the size of the group is, so as we said, it's the 5n. And just make an assertion that the GCD between the root and then is equal to 1. So we are checking if the number is indeed in the multiplicative group. Here we have the square root of side, this one. Here we go through all the powers of the root. So this G represents like the ith power. And here, as you can see, we keep multiplying G times the root, we make it mod n. So here we have all the powers until the square root. Then we go to the, how to say, so the new. This we can computing using the power mod. The root to the power, basically we want minus m, like that. And this will take n as well. Mod n or here G to the power minus m. So this should be still mod n. So basically here we want this part. So make the root to the power minus m and take this as remainder with n, or mod n. But because this is a negative number, we have to make sure it's a positive one, so we can just add phi to it. Because as we know, we can keep adding phi as much as we want because of the theorem we had here. So yeah, this theorem. So here we can keep adding, so whatever number we have here, we can add always a value 5. So here, because it's negative, we will add this 5 to make sure it's a positive 1, so it works properly in the comma. So here we have this. And also here we go to all the cards. This J has to start this time with A. And the A will keep also multiplying. This means here we check if the cards match its element with the A. So basically, if you're not familiar with the C++ syntax, this just means that we found the element A in the set. Here we have the int J is A. We already have the I here. So here we have K, which is the solution to our problem, which is those, just to make sure I'm not mixing up the nj. We want to check p for new size equal to p for j. This means that is equal to g for mi. Actually, it's the other way around. And here we can just return this thing. So if it's since this root is it's a primitive root, so there exists actually exactly one k. So this k is unique. So once we find it, we just like it. Here we actually can say it. So we shouldn't reach this part because it means we didn't find the solution. It shouldn't happen. So here we can say 13 and a is. We want to find the discrete logarithm of 6, modulo 13. So here we can so we would print the first, so the discrete log. So we'll give it the find root, just takes the non-label. Done. Or you actually need the root just to print it nicely. Here's the root to the power of k. I defined in the slides. So root to the power of k is equal to a mod. So the files like called size here. This g here, I don't know. Just reset and hit the answer. So here, as you can see that, so we get the root of 13, which is, so here the phi is 12, and we take the root is equal to 5. Uh, so here we take the 2. Yeah. we Here I removed the print statement here that used to print the value of the root. Um, so as you can see, here's the discrete logarithm, and we have this equation. So 2 to the power 5 is equal to 6 mod 13. In this we can already see that 2 to the power 5 is 32, and if we take the nearest multiple of 13, it's the 26, so the difference is 6, as expected here. So basically this is how we find the discrete logarithm of a number. So I hope this was clear, this lecture. I think it was a bit intense. So thanks for listening, and you can send me if you have any questions. Thank you.